Okay, my goal today is to teach you how to use this formula, the nth Taylor polynomial. And I'm going to write this formula in summation notation. Then I will explain that. It's sigma k from 0 to n f k a over k factorial x minus a to the power of k. So this is called the nth Taylor polynomial formula. And the goal of this is to approximate a function using polynomials. So here you have a very clear explanation of how you can get this and what is the Taylor polynomials. So the method that you can get this Taylor polynomial, and the idea behind that, you just basically you want to find a polynomial that will resemble the function you're dealing with, and you start by requiring that this polynomial at a certain value a is equal the value of the function, and then you require that they have the same first derivative at that point. Then you require that they have the same second derivative at that point, and then the third, and then you follow this logic, you get this formula. I don't want to go in the details for that because I will not ask you to prove this formula, but what really matters for you is being able to understand this formula and being able to use it. So first of all, I want to talk about the sigma notation. What is the sigma notation? The sigma notation is a summation notation. So imagine you want to express something like this: A1 plus A2 plus A3 all the way to, let's say, AN. Yeah, in math, this is a very, very long expression, and mathematicians don't like big notations like that. They always come up with shorthand notations to express this type of big expressions. And the notation for adding up some terms like these, and there is some pattern here, is summation notation. It's a sigma, uppercase sigma, and then you have AI, I from 1 to n. And this means that I, which is the index, is going to be first 1, then 2, then 3, and all the way. The last one is going to be n. And you can also use k. These two would be exactly the same thing. So k from 1 to n, a k. So it's customary to use I, j, and k for indices in the summation notation. You have seen this notation when we were working with the Riemann sum. Yeah, so it's not new to you. So when you look at this, k is going to be first 0, then k is going to be 1, then 2, then 3, and all the way, yes, to n. And then it would be the nth Taylor polynomial. So I also want to explain what these other things in this formula are. This one here is the derivative of the functions. It's the first, the second, the third derivative. The first term, k, is going to be 0. You're going to get f0 of a. You get f0 of a. And by f0 of a, we simply mean f of a. So that's the original function you're dealing with. And what is a? A is a number within the domain of that function. So any number that you can plug into that function and get an output. A is a number in the domain of that function. It's a fixed number. and you create your Taylor polynomial around that number a. What is f1 of a? That's actually f prime of a. So it's the first derivative of the function of interest at a. Then f2 a, that is the second derivative at a. f3, that's the third derivative. And generally, when you see, for example, fk of a, that's the kth derivative. That's the kth derivative of the function at a. Good so far? Any questions? So another thing that you see in this formula here, the Taylor polynomial, is k factorial. So what is k factorial? If you have, for example, 5 times 4 times 3 times 2 times 1, you can represent this with 5 factorial. So generally, if you have n factorial, that would be n times n minus 1 times n minus 2 all the way to 1. So that's the shorthand notation for when you're multiplying numbers from a certain number successively back to 1. Or from 1 to that number, doesn't matter. In any order, you can write this one. So for example, if you see 3 factorial, that's basically 3 times 2 times 1. There is a convention here, and the convention is that 0 factorial is equal 1. So that would be the convention that when you're working with factorial. So 0 factorial is going to be 1. 1 factorial is just 1. 2 factorial is 2 times 1, that's 2. 3 factorial, that's 3 times 2 times 1, that's 6. 4 factorial, that's going to be 4 times 3 times 2 times 1, that's going to be 24, and so on. And you can see there is an interesting pattern here. For example, if you have 5 factorial, that's basically 5 times 4 factorial. Or if you have, for example, 10 factorial, I can write that as, for example, 10 times 9 times 8 factorial. So generally, if I have n factorial, I can write that as n times n minus 1 factorial, because the n minus 1 factorial is going to be n minus 1 times n minus 2 all the way to 1. So that would be the factorial notation here. Is that clear what this is, the factorial notation? Okay, and here this is clear. It's x minus a to the power of n. And generally, the idea is that if you have a function that is not a polynomial, you can approximate it by a polynomial. And of course, the bigger the n is, the better your approximation. So before I continue, I just want to show you the curve here. So think of the red curve, the e to the power of x. That's the basic exponential polynomial. If you want to approximate that using polynomials, so first you have a polynomial of degree 0, which would be a straight line, a horizontal line. Then you have a polynomial of degree 1, which is this line here. Then you can have a polynomial of degree 2, which is going to be a parabola. Then you can have a polynomial of degree 3, 4, 5, and you can keep doing that until your polynomial matches the curve e to the power of x. And you can do this for any function. So you can just use any function and a series of polynomials to approximate the function using the polynomials. And what's good about polynomials? They're easy to work with, they're easy to derivate, they're easy to integrate. So this has lots of applications. So yeah, now I'm going to show you how to write that, how to expand it, and how to, and then give you some examples. So if I go back to this formula here, I just want to also write the expanded version of that. So imagine you have a function f of x, could be any function, and you have a number a that belongs to the domain of this function, and you want to write the nth polynomial, nth Taylor polynomial expanded around a for this function. So Pn of x. So first of all, k is going to be 0. So you get f0a over 0 factorial times x minus a to the power of 0 plus. Then k would be 1. You get f1 of a over 1 factorial x minus a plus. Then k would be 2. So f2 of a over 2 factorial x minus a to the power of 2. Then k would be 3. So the third derivative of the function at a over 3 factorial x minus a to the power of 3. So far I have, so up to this point I have a polynomial of degree 0. Here I have a polynomial of degree 1. Here I have a polynomial of degree 3. And I can keep doing that until I have a polynomial of degree n. So that would be the expanded version. But you can see what happens here. Some of them can be simplified. Like, for example, this one here, since the denominator is simply 1, and x minus a to the power of 0, anything to the power of 0 is also 1. So this is just 1, and this is also just 1. So what we're dealing with is the value of the function at a. Yes? So this first term is actually simply the value of the function at a. Yes? And that's why you have it here like this. It begins with fa. And then the second one can also be simplified a little bit because 1 factorial is simply 1. Yes. So you get the first derivative of the function at a times x minus a. So the first derivative of the function at a times x minus a. Then the rest of them cannot be simplified much. The second derivative at a divided by n, 2 factorial times x minus a to the power of 2, all the way to the nth derivative of the function at a over n factorial times x minus a to the power of n. Okay. Are we good so far? Now there is a special kind of Taylor polynomial. It's called a Maclaurin polynomial, and this is the same as the Taylor except for a is 0. So if you have a Taylor polynomial but a is 0, so this would be the formula for the Taylor polynomial, Pn of x, sigma k from 0 to n, f k a over k factorial times x minus a to the power of k. Now, if a is 0, so if you're writing a Taylor's polynomial for 0, for a equals 0, that is, you're trying to approximate the function for the values that are close to 0. Something that I think I forgot to mention is that when you're using this method of approximating a function, your approximations are going to be good for the value of a, or around the value of a. So for example, you can see here the values of the red curve are going to be close to the value of the blue curve, especially around 0, because in this one a is 0. So if a is 0, then you have this. You have sigma k from 0 to n, fk of 0, k factorial times, here a is 0, so you get x to the power of k. So if I want to expand that, it would be like this. The first term is going to be f of 0, then plus you have f prime of 0 times x, then you have f double prime of 0 over 2 factorial times x squared, then you have f triple prime of 0 over 3 factorial times x to the power of 3, and it goes all the way to the nth derivative of the function at 0 over n factorial times x to the power of n. So this series here, this would be called a Maclaurin polynomial. So in the exercises that you have in the web work, if you see Taylor series, then a is always given, and you are supposed to expand the series or expand the polynomial around that a. But if a is not given and it says expand the Maclaurin series, then it simply means that a is 0. And actually, for example 1, we are supposed to write a Maclaurin series because it's asking us at x equals 0. So in many instances, the Taylor polynomial provides us with a good approximation of x near x equals a. So, but if a is 0, it has another name. So it's basically exact same thing with a new name for a special case when this a here is 0. Okay, so let's try to, I'm going to show you an algorithm, a way of writing down this polynomials. So it says find the Taylor polynomial P1, P2, P3, and P4 for the function e to the power of x at x equals 0. So a, in this case, is 0. So that simply means that we need the first derivative, the second derivative, we need all the derivatives of this function up to the fourth derivative. So we're going to do this. We begin with the original function, f of x is e to the power of x. And for this function, we are lucky. The first derivative, the second derivative, the third derivative, all the derivatives are the same as the original function. So the first derivative, this would be the original function, which I can write as f0 of x. Then f1 of x, which is the first derivative, is also e to the power of x. The second derivative of the function is also going to be e to the power of x. And generally, I can see that for this function, fk of x is going to be e to the power of x. So all the derivatives are the same. They're all e to the power of x. Right? Now let's take a look at the formula. We have Pn of x is sigma k from 0 to n fk of, if I want to write the Maclaurin one, where a is 0, 0 over k factorial times x to the power of k. Okay. So for this problem, I can see that all of these are going to be e to the power of 0. So because fk of 0 is going to be e to the power of 0, which is going to be 1. So I can just replace this with 1 and I'm done. It's sigma k from 0 to n of 1 over k factorial x to the power of k. So now if p is 1, that means n if I want to write P1, that means n is 1. So P1 or P1 of x, notation for the first order or the linear polynomial for e to the power of x. That means it goes from 0 to 1. First k is 0, then k is 1. Yes. So I get, when k is 0, I get 1 over 0 factorial x to the power of 0 plus 1 over 1 factorial x to the power of 1. So that's going to be 1 over 1 times 1, 1 plus x. So that's my first polynomial. Then p is 2. Another notation would be p2 of x. So it's going to be 1 plus x, just like these two that I have. Then I also have the situation where k is 2. If k is 2, what do I get? I get 1 over 2 factorial, which is 2, x to the power of 2. So that's the next polynomial. Then if I want to do the same thing for when n is 3, so the previous one are not going to change. So P3, which is also noted by P3 of x, is going to have the same 3 terms, 1 plus x plus 1 over 2x to the power of 2. And then in this formula here, I'm going to plug in k equals 3. If k is 3, what do I get? I get 1 over 3 factorial. And 3 factorial is 3 times 2 times 1. So it's 1 over 6, x to the power of 3. So that would be the next one. If I want to get the next one, P4 or P4 of x, that's going to be 1 plus x plus 1 over 2 x to the power of 2 plus 1 over 6 x to the power of 3. Now I have 1 over 4 factorial, which is 24 x to the power of 4, and so on. And here you can see the effect of these. The first order polynomial is a line. It's actually the tangent line to the curve. Then you get a parabola. And as you can see, the bigger the n becomes, the better the blue one, which is the polynomial, is going to match to the function f of x. And then you can use the polynomial to approximate the original function, especially around 0 in this case, because a is 0. See, around 0, the polynomial and the function e to the power of x almost match up. So they have the same values. You can use the polynomial to approximate e to the power of x. So for example, if you're wondering how your calculator calculates e to the power of, let's say, 0.1, calculators use Maclaurin series and the Taylor series. So the calculator, if you say, for example, I don't know, e to the power of 10, it's not going to raise e, which is a crazy number, to the power of 10. That's going to take a long time. But it will use a Taylor series centered at 10 in order to approximate e to the power of 10. Make sense? Do you understand example 1? So there is an algorithm to this. The first thing you need to do is find the derivatives. So if, for example, you want to know up to P4, you will have to find the derivatives up to the 4th derivative. You have to take the derivative and then the derivative of the derivative and then the derivative of the derivative. And you should look for a pattern there. So for this first example, the pattern was so simple. It was the same thing all the time. But then you have to plug in the value that the Taylor polynomial is centered at, and calculate those values, and then you would just plug in the values into this formula. Okay, so I don't remember whether the formula is given in the formula sheet for the Taylor polynomial. So we can check that out. Yeah, it's here. So the Taylor polynomial formula is also given here. So you don't need to memorize the formula. So in order to write this, you will need to find f of a, f prime of a, f double prime of a over 2 factorial, f triple prime of a over 3 factorial, all the way to the nth derivative of the function at a over n factorial, and that's it. So let's do some more examples. But you definitely need to practice this a lot because it's not very easy. Okay, so let's look at the problem that is a little more difficult. Find the nth Taylor polynomial for the function, so f of x, which is the same thing as f0 of x, that's the original function, is 1 minus x to the power of minus 1. 1 over 1 minus x, that's the same thing as 1 minus x to the power of minus 1. And we want the Taylor polynomial to be centered at x equals 0. So a is 0. And if a is 0, we're dealing with a Maclaurin series. So that is, it's going to be like this. Pn of x is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared, and all the way to f n of 0 over n factorial times x to the power of n. So what do we need? Here we need to find a pattern, because it's not asking us to find, I don't know, the first, the second, the third one. It's asking us to generally write the nth Taylor polynomial. So I'm going to take the derivative of this function until I see a pattern in it, and so that I can write a formula for fk of x, and then I can use that formula in the Taylor polynomial. Okay, so the first derivative of this is going to be minus 1 minus x to the power of minus 1. And then I have to multiply with the derivative of the inner function, which is going to be minus 1. The derivative of 1 minus x is minus 1. And I have to use the chain rule here because I have a function to the power of some negative number. So it's going to be negative 1, 1 minus x to the power of negative 2. I wrote negative 1, negative 1 minus 1, negative 2. And then I have to multiply by the derivative of the inner function. So this becomes 1 minus x to the power of minus 2, right? It becomes positive. And then when I take the second derivative, it becomes minus 2 times 1 minus x to the power of minus 3, and I have to multiply by the derivative of the inner function again, so it becomes 2, 1 minus x to the power of minus 3. Let's keep doing that. The third derivative of the function at x becomes minus 3 times 2, times 1 minus x to the power of minus 4 times minus 1. So it becomes 3 times 2 times 1 minus x to the power of minus 4. So I hope you can see the pattern here, but I'm going to do one more so it becomes more clear. You're going to get minus, take the derivative of this, minus 4 times 3 times 2 times 1 minus x to the power of minus 5, which will become times minus 1, which will become again positive. 5 times 4 times 3 times 2 times 1 minus x to the power of minus 5. So I hope that now you can see the pattern that generally the kth derivative of the function is going to be, so you see the fourth derivative gave us 5 factorial. The third derivative gave us 3 factorial. So yeah, there is no 5 here, it's 4 factorial. I don't know why I wrote 5. There's no 5. It's 4, 3, 2, yeah, and then 1 minus x to the power of minus 5, and then the minus 1 and the negative cancel out. So the fourth derivative gave us 4 factorial. The third derivative gave us 3 factorial. So it's going to be k factorial. And then there is a 1 minus x to the power of, here, this is negative n minus 1. So if, for example, if you have, negative k minus 1. So if k is 4, it's going to be negative 4 minus 1, negative 5. If k is 3, we're going to have negative 3 minus 1. That's minus 4. If k is 2, we're going to have negative 2 minus 1, negative 3. So this is going to be negative k minus 1. So this is the formula that I found for the kth derivative. At this point, if I plug in 0 into this to figure out what fk of 0 is, I'm going to get 1 to whatever power. 1 to whatever power is going to be 1. So I simply get k factorial. Is that clear? Okay. So now let's just put that in the formula. So the formula is Pn of x is sigma k from 0 to n. And here on top we have the kth derivative at 0 over k factorial times x to the power of k. So I would just need to plug in what I found for the kth derivative of 0 into this. What I found is the kth derivative, the k factorial. So it's going to be k factorial over k factorial. It's going to be like this, sigma k from 0 to n, k factorial over k factorial x to the power of k. So this is just 1. So I get x to the power of 0 plus x to the power of 1 plus x to the power of 2 plus x to the power of 3 all the way to x to the power of n. Yes, which is the same thing as having 1 plus x squared plus x to the power of 3 all the way to x to the power of n. So that's how you get this. So for example, generally for n, you get 1 all the way to x to the power of n. If you want to know the fifth Taylor polynomial, or in this case, Maclaurin polynomial, because the a is 0, then you just need to go up to 5. It's 1 plus x squared all the way to x to the power of 5. And now we can test this. So the original function was f of x is 1 over 1 minus x. So we can calculate the value of this function at a number close to 0 using a calculator. And then we can also calculate the value of this function using the polynomial, approximating the value of this function using the polynomial to see whether they're actually close or not. So the number that has been used is 0.1. So if you plug in 0.1, into the fifth Taylor polynomial, that is 1 plus 1.1 plus 1.1 squared plus 1.1 to the power of 3 all the way to 1.1 to the power of 5, you're going to get this number. If you plug in 1.1, if you plug in 0.1 directly into the function, into the original function, into this, you're going to get 1.1111 forever. So you can see how close they are. That's because we are using a rather high order polynomial, the fifth order polynomial, in order to approximate this function. So in this example, it's not obvious how this is useful because it's actually easier to use this, the original function, to figure out what f of 0.1 is rather than using the polynomial. However, if you have a function like e to the power of x, or if you have a function like sine x, like cosine x, like tangent x, it makes a lot of sense to try to figure out the values of these functions using a polynomial rather than the original function. And if you're using a high order polynomial, like the calculators and computers do, then you get a very good approximation. Like in this case, the error incurred in approximating f of 0.1 using this fifth order polynomial is a very, very small error. Any questions? Okay, then. Now let's take a look at one applied example of that. So imagine you want to calculate root 26.5. You want to calculate the root 26.5 using a polynomial. So this is our goal, calculate the root 26.5 using a polynomial. What we know is that root 20, this is the closest perfect square to this number is 25, and root 25 is 5. So that we know. And in order to have root 25, we need to use the function f of x equals root x, and x needs to be 25, because if x is 25, then this is actually the a. If we use a 25, or if we expand the polynomial, the Taylor polynomial centered at 25, then that's going to be the closest perfect square to 26.5, the number that we're trying to approximate. So it says, obtain the second Taylor polynomial. So since we are using the second Taylor polynomial, it will be a quadratic polynomial of degree 2 for this function, centered at x equals 25, and then use it to approximate root 26.5. But I was just trying to explain to you that if I'm not given f of x, if I'm not given that x must be centered around 25, you should know that just by looking at the problem we're trying to solve. So if the problem is find an approximation for this. Yes, then it's evident that the function is going to be f of x is equal root x, because it has root of a number. So the function is going to be f of x is equal root x. And then what should that function be centered at? It needs to be centered at 25. That is, a needs to be 25, because 25 is the closest perfect square to this number. So I'm going to give you another example. If I want to figure out what is root 9.1 using this method. From this problem, it's evident that f of x needs to be root x, because that's the function here, root of a number. And then I need to center it at 9, because 9 is the closest perfect square to this. And I can easily get the value of the function at 9. I can easily get the value of the first, the second, the third, all the derivatives at 9. Another example. If I ask you to give me an approximation for sine of 0. Let's say 0, 1. So sine of 0.01 radians. Yes. Then, of course, the function that you're trying to write the polynomial for should be the function sine x. And then you think about the closest number to this number for which you know what sine is, or what the derivative of sine is in that is at that point. Yes. So the derivative of sine is cosine. The derivative of cosine is going to be minus sine. So we have to center this at 0, because this number is very close to 0. 0.01 is very close to 0. And also, I can easily figure out what sine of 0 is, what cosine of 0 is. Sine of 0 is 0, cosine of 0 is 1, and then the derivatives, any ordered derivative of this function, I can easily figure out the value at this point. Yeah, so these are the criteria. You have to look for a number that is close to the number you're trying to approximate. And also, it should be easy to find the derivative, the value of the function or their derivatives at that number. And we're not going to go beyond this. I think all the examples that you have are with root functions. So basically, the function is going to be root x. And then you ask yourself, what is the closest perfect square to that? So if it's 26.5, 26.5 is between 25 and 36, 5 squared and 6 squared. So the closest number that is a perfect square to 26.5 is 25. So you're going to center your polynomial at 25. Okay, so now let's try to figure out the approximation here. I'm going to read the problem again. It says, obtain a second Taylor polynomial for this function centered at 25 and use it to approximate the value of this function. So the second order Taylor is going to be P2 of x. It's going to be f of a plus f prime of a times x minus a plus f double prime of a over 2 factorial, which is just 2 times x minus a squared. So the only thing I need to do is to figure out f of a, f prime of a, and f double prime of a, and in this case, a is 25. That's all I need to do. And then I plug in the values. So f of a is going to be root 25, that's going to be 5. F prime of x is going to be, since f of x is root x, the derivative of that is going to be This is like having x to the power of 1 over 2. 1 over 2 x to negative 1 over 2. And I also need the second derivative. So let me just figure it out right now. I'm going to get minus 1 over 4 x to the power of negative 3 over 2. Yes. So this I can write as 1 over 2 root x. And this one I can write as negative 1 over 4 x to the power of root x to the power of 3. Yeah. So notice that if I have x to the power of 3 over 2, I can write that as x to the power of 1 over 2, that to the power of 3. I can write that as root x to the power of 3. So if I need f prime of 25, I would just need to plug in 25 into this. I get 1 over 10. And if I need f double prime of 25, I would just need to plug in 25 into this. And I would get, that's 5 to the power of 3. That's 125 times 4. I get negative 1 over 500. Is that clear? So I just need to plug in 5 goes here, 1 over 10 goes here, and negative 1 over 500 goes here, and I'm done. So I get 5 plus 1 over 10 times x minus 25, because a here is 25, 25 goes here, plus negative 1 over 500. Let me just do that using the equation that I have over here. Okay, so P2 of x is going to be f of a is going to be replaced with 5 plus f prime of a, that's 1 over 10 x minus 25, because a is 25. And then I have minus 1 over 500 times 1 over 2, because there is the over 2 here. There is already over 2 here, times x minus 25 to the power of 2. And if I simplify that, I get 5 plus 1 over 10 x minus 25 minus 1 minus or plus minus 1 over 1000 x minus 25 to the power of 2. So now I can plug in order to approximate f of 26.5, which is root 26.5. I can plug in 26.5 into P2 of x. I will get an approximation for this, just using a polynomial, which is going to be easier to work with. So imagine you have a basic calculator, you can multiply or you can add up, but you cannot take root. Yes, and then you can use this formula, just plug in 26.5 into this, and you will get an approximation for what root 26.5 is. So the actual value of root 26.5 rounded to 5 decimal places is this, and you can see that these two are really close. So even just using the second order polynomial, we got a very good approximation. Okay, so I'm gonna let you to work on the exercises from this set. I have already opened the set 11.1, and this section needs a lot of practice. So definitely uh, practice finding those series of derivatives and looking for the pattern in that series of derivatives so that you can find the formula for fk of x. So this needs a lot of practice. And here we have 16 of them. There are also problems in the book that you can do in order to get more practice. For now, I want you to start working on these problems and let me know if you need help. There is something I need to mention about these problems. Uh, the terminology here could be a little different. So let me tell you, what does this mean, quadratic approximation and the linear approximation. Whenever you see linear approximation, it simply means you approximate f of x using p1 of x. So p1 of x is going to be a linear function. It's going to be a polynomial of degree 1. And whenever you see quadratic approximation, that means, so I have to say actually not exactly equal, but almost equal. You're trying to approximate f of x using the second order polynomial. So whenever you see linear approximation, that is using the first order Taylor polynomial, and whenever you see quadratic approximation, that would be the second order. And of course, if you see cubic approximation, then you are approximating f of x using the third order polynomial. So for this problem here, you have this function f of x. X0 is equal 0. So in some books, they use x equals 0. In some books, they say x0 is equal 0. It's basically, it means that it's a Maclaurin series. That is, it's going to be centered at 0. And for this one here, you write the P2, and for this one here, you write the P1. I'm going to give you a few minutes to work on this problem, and then I'll do it as an extra example. Okay, guys, let me take care of this one for you. F of x is e to the power of minus 4x. I would need the first and the second derivative. I would need the first derivative for the linear approximation, and I would need the second one for the quadratic approximation. So let's take the first derivative of this function. We get minus 4 e to the power of minus 4x. And then the second derivative is going to be 16 e to the power of minus 4x. So if I now plug in 0, because notice that we want to find these approximations around x equal 0. So I need to plug in 0 into all of them. If I plug in 0 into the original function, I get 1. If I plug in 0 into the derivative, I get minus 4. If I plug in 0 into the second derivative, I'm going to get 16. And then let me just write down the formulas for P1 and P2. P1 of x is going to be f of a plus f prime of a times x minus a. And if a is 0, the Maclaurin series is going to be f of 0 plus f prime of 0 times x. And for P2 of x, the formula is going to be the first two terms are the same, f of a plus f prime of a, x minus a. And then I have this term as well, f double prime of a over 2 factorial, which is just 2, times x minus a squared. And now if a is 0, this will become f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 times x minus a to the power of 2. Just x to the power of 2 because a is 0. X to the power of 2. Okay, so I have all the values that I need to plug in. So that's all I need to do. This one is going to be 1 plus the first derivative times x. So minus 4 times x. It's going to be 1 minus 4x. That's the answer for the linear one. And then for the quadratic one, it's going to be 1 minus 4x. So the first two are going to be the same. And then for this one, I get 16 over 2, which is 8, x squared. So 1 minus 4x plus 8x squared. Just let's preview the answers. For the linear, 1 minus 4x. For the quadratic, 1 minus 4x plus 8x to the power of 2. That's the 16 divided by 2 part. Is that clear?
Yes.
Okay, great.